equal to 2 times of B is very important. Now we learn simple, multiple and degree of vertices, and with this Sine-Hedge-Shaking theorem. The next one, path. To understand connecting all the vertices, we need these three basics. So first we'll learn about trial. Trial means starting, going on one by one and reaching one another vertex. Trial. So no edge can be repeat. A to B, B to C. So like this. Trial we are going one by one node. Another important one they used to call to understand path. Path means no vertex repeated. Here A, B, C, and then D, because there is a link, so we can go to C to D and D to E. There are many ways, but we can reach. Path means there is n vertices are different. Then we can say path. If the path again reaching the starting and ending vertices as a same, that is circuit that we'll see later. The last. So walk also we can say there is no restriction. Walk means as it is, we will walk everywhere. So you can take A, B, and then D, and then again A, again B.
Excuse
So
me, sir.
yes, madam.
Sir,
You are
PPT
able
not
to
showing, ma'am.
PPT
PPT
are
not
not able.
sharing, sir.
Hope to switch on. Now you are able to see me.
Yes, sir. Yes, sir. Now it's visible,
Oh,
sir. Thank you, sir.
okay, okay. So still now we saw some basics about set of vertices, set of edges. That is a technical word. But you can say point and relations and connection. That is a different word. But as a, mathematically, we used to take point as a vertex, link between two vertices as edges. So vertices in edges. Now I learned handshaking vertices formula. Now we learn path, walk as it is. Wherever we want, again we can repeat the vertices, edges. That is walk. Path means going vertices, edges like this. Vertex edge like this, one by one. If you go, that is path. If you start and end, any path start and end with the same vertex, that is called circuit. uh, Circuit or cycle, we can say. This is the basic things. Now again we'll see a graph. We can define V comma E is undirected graph with ABC as a two vertex. Suppose here they are explaining about cycle. If it is repeat, that is not cycle. Okay, this and all just by going through you can calculate. We'll go to the next one. Already we saw multi-graph. This graph contains parallel edges. So this is multi-graph without parallel edges, simple graph. So maximum in graph theory will deal simple graph. Now here we are going to learn subgraph. Subgraph is nothing but just deleting some set of vertices or some set of edges will get another graph, that is subgraph of graph. That is, if you suppose graph G, if you take G1, this is also subgraph of first graph. Just by deletion, so we will get subgraph. Here they are taken only A, B, C, D, just like cycle. Okay, these are all subgraph of the first graph. So first subgraph, by a definition, all the vertices and edges belongs to G. This is H1, suppose subgraph 1, subgraph 2, subgraph 3, all the subgraph, set of edges, set of vertices belongs to the main graph. Likewise, we can split. So any graph, even without edge, it will take only vertices, that is also subgraph. But here edge set is null set. Here another structure, important structure in graph theory, complete graph. Complete graph by using notation K, capital K with the suffix n. Here you see K5. So complete graph means there is a edge between every pair of vertices. That is K5. This is, we can say K3. Okay, here also everywhere edges. But this is not complete graph. This is just the graph. Here they shown K3 as KC3 also we can say, because this is just like cycle with 3 vertex, 3 edges. Okay, now we learn complete graph. Complement graph, just taking region as a vertices and vertices as a edge, that we'll see later in detail. Now, one more we got to learn isomorphic. Isomorphic means, we'll see next slide, I think better. Yeah, we'll take these two graphs. You see, these two graphs are indicate same A, B, C, D. Here also A, B, C, D, but given different vertex name 1, 2, 3, 4. But even though here one is each and every vertex we can map with corresponding vertices in another graph. These three are isomorphic graph, but mentioned in different form with a different name. Here 1, 2, 3, here A, B, C, D, here W, X, Y, Z. But shown in different form. Here see 3 vertex, 3-degree vertex is 4. Here also all the 4 vertices are degree 3. So both we can say isomorphic. First one and third one also isomorphic. Second and third, so mutually all isomorphic graphs. The same example, these two also in different form. This they used to call Peterson graph, but here shown in different form, but still both are same number of vertices with equal degrees. So isomorphic graph. This is also isomorphic graph. Here shown in different form. Here shown in just like a triangle form. Okay, this is also isomorphic. So any graph we can draw in different form that indicates same meaning. It is allowed to draw in different form, that is isomorphism graph. Already we saw this simple formula. Now I think learn basic thing, just going through you can learn. So generally people used to say by Euler. Euler is the first mathematician. He introduced all science and philosophy, everything. He is the first person introduced all the subject initially. So one day what happened in his area, 7 bridge conics Königsberg Bridge problem in Borussia. We used to take rest or walk in the evening for leisure time. There are two islands, two banks of rivers. He took as a one graph. He tried to travel each and every land by crossing only one time each bridge. Is it possible or not? Is not possible. Then he gave one concept, any graph with even degree, always possible to cross. With that, he presented one conference about this logic. Like that, they used to say the graph theory started from this, but the later on is developed as a computer concept by using mathematical concept when to how to operate, how to calculate computer for different tasks that happen. So the Euler trial, they will say what he said that if you traverse every edge of graph exactly once, that is Euler trial. So each and every edge exactly once, and you are able to reach the same point, then that is Euler circuit. So here mention Euler circuit. This Euler path starting and ending after crossing all the edges. But with this graph, not possible to cross. Okay, this is not Euler graph. Wherever the graph, you are able to travel all the edge and reach the same point. That is Euler graph. That given in different form. That is Euler trial means just walking and reaching. That is Euler trial. Reaching the same point, Euler circuit or Euler cycle. Anyway, we can say. These are all given some examples. Here you see an Euler trial exists in any graph G if G is connected and has exactly two vertices of odd degree. Trial means not a cycle. You can start with one vertex, will end with another vertex after reaching the all edges. So in that definitely two odd degree vertices because that is the end. So for example, if we take AB, if we travel A to B, A and B are odd degree. Okay, we can assume lot of vertices between A and B, maybe A1, A2, AN. Here, another theorem they are given, directed Euler circuit exists. Directed Euler circuit exists. If a circuit exists, G is connected the in degree, out degree for all vertices. So if Euler circuit exists, so each and every vertex must have in degree, out degree. So one edge will enter, one edge will leave from the vertices. That is the one of the concept. So already we learned about degree. We'll go to next one. Next one, planar graph. So planar graph is very important nowadays because VLSI circuit by using algebraic concept, topological concept, linear algebra, we have to draw a graph without edge crossing. See definition, a graph, a graph G is called planar if G can be drawn in a plane with its edge intersecting only at vertices of G. So edge should not cross itself. So whatever the edge start always with one vertex and reach to another vertex. See in this graph, but this is not allowed. But here they are given, even though given in outer, without this edge we can say planar graph. Okay, K phi is not planar because lot of edge intersects. But To remove intersection, they're shown outside, but it's not allowed. In circuit, not possible. Okay, so without this edge, you can say this K4 minus E. K4 minus E, we can say planar graph. So planar graph means edge directly will not should not intersect. It always intersect at the vertices, end of the vertices. This is always used in VLSI routing and plumbing. Uh, uh, these are all the applications. Next, the planar graph in different form. Bipartite. This bipartite means the graph have two set of vertices. One set in one group, another set in another group. This we can say bipartite graph. But edge should not travel between the same group, but edge should connect opposite group. Then we can say bipartite. Each and every edge connected. See, this first one connected with all the four. This is K44. Second one also connected with all the four opposite group. Then complete. Otherwise, simply bipartite. Bi means two set. Same way we can say tripartite, complete tripartite, like this n partit we can say. Depends upon application. So maximum always use in the application only bipartite, that to complete bipartite. As a best example, they will say one group has source, another group has sink. That means all houses. These are all production places. Each and every people they will use whatever the product the society happen, we need. So that need given by link. See, to understand about bipartite, one part always production side, another part always consumer side. Say, okay. Same way, tripartite. Some product will go to another company also. One company product will go to another company. In that way, we can say tripartite. This one K44, here K33, but this is not planar graph. Because just to understand they taken edge outside, but this is not planar. So now you will learn planar graph and bipartite graph. To understand here also given. So deep discussion no need, we'll go to another topic. The Krudowski's theorem. He discussed about planar graph. That's why this theorem we are saying with this author name. A graph is planar if and only if it contains subgraph that is homomorphic to either K5 or K33. A graph is planar if it contains as a subgraph homomorphic to either this or that. Here you see, even though edge crossing, this subgraph they are able to split without edge crossing, they are shown. But yeah, outer is actually not allowed. Yeah, we'll go to the next one. Already we learned K5, K33 is not planar graph. Peterson graph, even though if you remove intersection, but it's not allowed like this. A circuit we cannot create parallel way. Okay, that is non-planar. This is also discussed about planar. Another important formula regarding planar. See, in any graph, number of vertices minus E plus R. R is number of regions. You can say this is one region, this is one region, outer one region. Always equal to 2. V minus E, this is one of the basic formula derived by Euler with respect to connected planar graph. Here given V as number of vertices, E as number of edges. Next we will see, they here verified this formula with a different graph. Here no edge, here one edge, here one edge with two vertices. They verified, still we are able to get 2. Okay, applying this formula, we will get 2. Here, about planarity, here we discuss. So basics you learn. So from this you can go through easily about in application of planar graph in different form. Again they verified the same formula for different. Yes, now we will see Hamiltonian path, Hamiltonian cycle. A path or cycle that contain every vertices. In Euler, he defined paths would contain all the edges, but in Hamiltonian, he described a path or cycle that contain every vertex. Then we can say Hamiltonian path. If you start and end with the same vertex, Hamiltonian cycle just by containing all the edges. Seen here given in dark line, this is Hamiltonian cycle. Same way you can practice Hamiltonian path cycle. Okay. For any graph, how many number of uh, Hamiltonian cycle or path, which is non-polynomial time, which is not easy to find, but we can find one. But how many possible? That's like a permutation combination. It will go. It will take time, lot of work, and no need. So again, with another graph, Hamiltonian path, Hamiltonian cycles, you can draw in different cycles by approach starting with any vertex x, y. Okay, you can practice by taking this graph. It's given with another example, Hamiltonian path, Hamiltonian cycle. They mention here. So now you learn what is Hamiltonian. It's include all the vertices. From previous graph, they mention here. You go to, there's a lot of example there given. Okay, Pauline, coloring, after seeing coloring, we'll see. I will go to next slide by closing this. So I have one more slide about basics. So I introduced play up to planar graph, Hamiltonian, Euler. So now you see with that basic concept,
Sir, your voice is not audible, sir. Suraj, sir, your voice is not audible, sir. Sir, voice is not audible, sir. Silveraj, sir. Silveraj, sir. Silveraj, sir.
Yeah, now?
Audible, sir. Okay.
Yeah, yeah. Yeah, anyway, seeing one by one all the basics of graph, it will take time.
Okay, okay.
So straight away, I'm going to do basically very important algorithm. Whoever says graph theory, they must know about Kruskal's and Prim's algorithm. This is to find for any connected graph, tree, a tree should contain all the vertex. So that's why this is so minimum spanning tree. The application of Hamiltonian graph. Okay. Now you see, we used to connect all the computers in an obvious building using least amount of cable. Same time, we should not repeat okay connection. That we'll see now. So just I will explain. Tree is a connected graph without any cycle, just to start and end with one vertex. There are different type of tree, but here in connected graph, we are going to take only tree. Tree means without cycle. That is called spanning tree. This how to find. The minimum spanning tree means they are possible to get for any connected graph n number of spanning trees. If you weight is given, you have to take minimum weight tree graph, that is minimum spanning tree. Here and here there are a lot of vertices, edges. We are going to choose only minimum edge. That is edge, you can say bridge, edge, and the distance or traveling cost we can consider as a weight of that edge. Here. Now we'll see minimum spanning tree, the basic algorithm. We have to find a tree. Connected graph maybe have any cycle or loop parallel. Within that set of vertices, we have to find tree graph. Out of that tree graph, if it is weighted tree graph, we have to find minimum weighted tree graph. So Kruskal algorithm first we'll see each vertex is in its own cluster. Cluster means everywhere available. It's maybe inside connected graph or self loop or parallel, whatever it is. But here you have to take all the edges one by one we got to here instead of reading all, first we got to arrange all the edges in ascending order. Just start with the smallest edge and connect as a tree, spanning tree, going on taking next least weighted edge. So yeah, because we started with the minimum, going by one, while connecting edge, we should not make any cycle. If it is made cycle, we have to leave that edge up to, we have to pass through all the edges. Finally, we'll get minimum weighted tree, that is spanning tree. Minimum spanning tree, that is called minimum spanning tree. So here given that is each and every vertex we have to arrange in ascending order. So you can go through smallest weight to the greatest weight. Here given example, here smallest, here you will take this example, smallest weight is 1. You can see one by one. So this is the minimum. Suppose here not given, but by arranging in ascending order, the least one, we'll choose first one, then next two, next we have to choose next two, and then next another one more two is there. If you choose, still there is no cycle. But if you choose three, so one more two is there, you can choose. Still there is no cycle. But if you choose another three, it will make cycle with this edge. So we have to leave that one. Then we'll choose another three, another next least weighted edge. So likewise, you see finally we reached one tree graph without cycle. But previously you see this graph with a lot of cycles. Now the end graph with the trees. This spanning tree is the minimum weighted tree. That is minimum spanning tree. Okay. If you add 1 plus 2 plus 3 plus 2 plus 2, that is the weight of this spanning tree. This calculation will occur m into log n because m vertices, that is order of m, but each and every vertices we use to search where to take next one, that is order of log n. Each and every one involve log n time, that is the order of log n. It's given as a code. We'll go to next one. Prim's algorithm. In any textbook you will get all the steps. This is also same. You see, you will take same graph. If you apply Prim's algorithm, how will get spanning tree? You see, one by one, we'll choose here vertex. Okay. There we used to choose edge. Here we used to choose first vertex. From any vertex, we can take minimum weight. See, minimum weight is here. There are out degree 4, 2, 6, 5. Among with 2 is the least, we have to choose 2. Then leaving remaining, this is the chosen. Then next one, 1 from this. Okay, we should not choose from again A. We got to choose from E. Again from D. Again from D, another one. So again we get the same minimum spanning tree. Previously we used to travel by edges. Here we traveled by vertices. That is the difference between Prim's and Kruskal. So this is also same way it happen order of m log n. So this is also indicate just like Prim's algorithm. I will go to next one. Okay, if you learn Kruskal and Prim's algorithm, this is enough. In discrete mathematics also everywhere we use. Now I will take another slide. Is all of you able to see this slide? Third one.
Sir, not audible, sir.
Ah, yes. Now you able to hear? Here,
Yes, sir.
beta
Yes,
labeling
sir.
called as graceful labeling. A function f is called graceful if f is injection means into function from the set of vertices to the set 0 to m. Because graph with m edges 0 to m we have to take. For edge labeling we have to collect absolute difference, positive value of difference of end vertices. For any edge uv, f of u minus f of v will get another labeling. So this is also distinct. So here given vertex labelings also 0 to m we are given as different labeling. Edge labeling automatically will get just by subtracting end values. This this labeling is called graceful. If any graph able to give such a labeling, that is graceful graph. Okay, now this you see this is one of the example. They are given for vertex. There are 15 edges. You can choose number from 0 to 15. Here given 0, 15, here 1, 4. Now you subtract here 1. So vertex also different labeling and edge also received different labeling. With this order, we can say this is graceful labeling. Just simply if you take any triangle, we can start 0 to 3. 0, 3, 2 will get all the labeling 1, 2, 3 like this. So vertex can receive 0, but edge only 1 to m. The same labeling, graceful labeling, we can call it as alpha labeling. if any edge possible to have some smallest number lambda, that lambda lies each and every edges, then that type of graceful labeling is called alpha labeling, alpha valuation, okay, or alpha graph. Here they have taken grid P4, P5, partition product of path P4, path P5. In this also as usual given starting with 0 and highest level, going on reducing, finally we'll get the edges with 1 to 31. This is one of the labeling. Then you see another theorem. If a graph G with Q edges alpha labeling, this can be decomposed from complete graph that complete here n value 2 CQ plus 1. C is some constant, any 1 or 2 or any number. From that we can decompose isomorphic subgraph of G. Okay. So if it is alpha labeling, there wrinkle given in general, any tree can be decomposable, but here he given any alpha labeling that can be decomposed from this complete graph with the 2CQ plus 1 vertices with the 2CQ graphs. That many graphs you can see. Same way, another people also, Sanati and Bandan, given with the complete bipartite graph. For a complete bipartite graph, this alpha labeling can be decomposed. These two theorems are very, very basic. In case of labeling, here given cyclic decomposition, K3. Here they taken path with the, 3 vertices. This is removed like this, next to this one, then next, like this. One by one, we are able to remove 5 times. Same way, the more important theorems are given by different people. Just by taking labeling subject, you can learn. We introduce one subdivision. Subdivision means any edge. We have to introduce one vertex, but here we introduce one graph just by removing each edge by K to Mi. The two part is end vertices UV and M part is the middle edges. This we used to call super subdivision. Why we introduce even any different structure we can make as a alpha labeling or graceful labeling. Suppose if we say cycle, we can introduce here M is 4, here M is 5, here M is 3, here 3. Any combination, infinite number of combination. We can start with 0 and continuously we are able to give graceful labeling. That is the specialty of this theorem. For any non-trivial connected graph, just by introducing super subdivision, that will admit alpha valuation. If admit alpha valuation, definitely that is graceful graph. Any structure is given, this algorithm we used to say breadth first algorithm. If you choose any one vertex, nearby vertex we have to give labeling 1, 2, 3. That is base labeling. After that we have to introduce C 0 nearby only 1 1. 1 have 3 2 nears, 3 neighbors, 2 here, 3 here, 4 here. This is called breadth first algorithm. Then we start with 2 with incident with this, 2 vertex. So here you can give 5, 6, or here 5 or here 6. After giving this, I'm going to introduce that super subdivision each and every level. Then you're able to give, this is a labeling algorithm, algorithm third. For at one level, we are able to give many extensions. Okay. So that given a single graph, we gave labeling as a mathematical equation at ith level with super subdivision. How many super subdivisions will give? This is proved as a theorem. Finally, we are able to give graceful leveling starting with 0 and the highest to 86, 88, yes. So by subtracting 87, 88, 87 like this, finally we'll get 1. This is 1. See, this is between 8 and 9. This 8, if you see everywhere, every edge, between every edges, there may be 8. That is called alpha. Condition for alpha. It is graceful graph. We are able to create infinite number of choices just by going on changing m value for each and every edge. So we proved this one in general. So they appreciated. After giving supersubstitution, every graph will become bipartite. Bipartite graph easily can give graceful leveling, automatically alpha leveling. Satisfies. So now it's for 11:40. I will stop with this.